In the first lecture, we used GCD as an example to introduce some basic concepts in programming. We will continue to look at the same example and see how to refine our program and explore new ideas. Here was our basic algorithm for GCD, which, as we said, more or less follows the definition of the function. So we construct two lists of factors for the inputs m and n. So we construct fm, the factors of m, fn, the factors of n. And then from these, we compute cf, the list of factors in both lists or common factors. And our goal is to return the greatest common divisor or the largest number in this common list, which happens to be the last one in this list since we add these factors in ascending order. So can we do better than this? So the way we have proceeded, we first scan all numbers from 1 to m to compute the list fm of factors of m, and then we again start from 1 to n to compute fn. So an obvious improvement is to just directly scan the numbers from 1 to the larger of m and n, and in one scan compute lists fm and fn. In other words, for each I in this list 1 to the maximum of m and n, we first check if I divides m. If so, we add it to the list of factors of m. And then we check if I divides n, and if so, we add it to the list fn. So instead of doing two separate scans over 1 to m and then 1 to n and repeating the pass, we do it in one scan. But even this can be improved upon. If we are doing it in one pass and we are checking if numbers divide both m and n, why don't we just directly check for common factors? In other words, instead of computing two lists and then combining them, we can just directly do the following. For each I from 1 to the maximum of m and n, if I divides both m and n, then we directly add I to the list of common factors. If it divides neither, or if it divides only one of them, then it is not a common factor and we can discard it. In fact, notice that rather than going to the maximum of m and n, we should go to the minimum of m and n. Because once we cross the smaller number, we will not get a factor for the smaller number. Remember that the factors of m lie between 1 and m, and for n lie between 1 and n. So if m is smaller than n, for example, if we go to m plus 1, though it may be a factor of n, it certainly cannot be a factor of n. So our better strategy is, for each I in the range 1 to the minimum of m and n, if I divides both m and n, then we add I to the list of common factors. Here is a much shorter Python program implementing this new strategy. So instead of computing the lists fm and fn, we directly compute the list of common factors. So we let I range from 1 to the minimum of m plus m and n, and remember that Python requires us to give the limit of the range as one more than the limit we want to go up to. So we go from 1 to the minimum of mn plus 1, and now we have an extra connective. It's called a logical connective, and which says that we want two conditions to be true. We want the remainder when m is divided by I to be 0, in other words, I divides m, and we also want the remainder when n is divided by I to be 0, so I should divide both m and n, and if so, we add I to the list of common factors. And having done so, once again we are doing it in ascending order, so the common factors are being added as we go along, and the larger ones come later. So we finally want the last element, which in Python is given as the -1th element of the list cf. So having done this, maybe we can simplify things further. Do we need a list of common factors at all? Remember that we only need the largest common factor. We observe that there will always be at least one common factor, namely 1. So the notion of the largest common factor will always be well defined for any pair m and n. Each time we can start with 1, and each time we find a larger common factor, we can discard the previous one. We don't need to remember all the common factors, we only need the largest one. So this can greatly simplify our strategy because we don't need to keep the list of every possible common factor in this list. We just need to keep the largest one that we have seen. So we can use a name, say MRCF for the most recent common factor, and keep updating this name with the value of the common factor that we saw last. So here is a Python implementation of this idea where we don't have a list at all. We directly scan all the possible common factors from 1 to the minimum of MNN. Whenever we find a common factor, we update the value of our name MRCF to be the current common factor that we have found. Now remember that 1 will always be a common factor. So initially MRCF will be assigned the value 1. It will not be that we go through this repeated execution of this and never assign MRCF because the condition is never true. Since 1 is a common factor, we will at least have MRCF equal to 1. But if we find a larger common factor, the 1 will be replaced by the later common factor. So at the end of this for iteration or loop, what we end up with is the largest common factor that we found between 1 and the minimum of MNN, which is indeed the GCD of MNN. So we can still do some further optimizations. Since we are looking for the largest common factor, why do we start at the beginning, which will give us the smallest common factor? So we can start at the end of the list and work backwards. So instead of running from 1 to the minimum of MNN, we can start from the minimum of MNN and work backwards to 1. Again, the guarantee is that 1 will always show up as a common factor. So if there are no other common factors, at the very end, we will find 1 as the greatest common factor. And in this process, we don't have to ever go past any common factor that we find. If we are working backwards from largest to smallest, the very first common factor we find must be in fact the GCD of MNN. How would we write this in Python? Well, you can modify that for I in range. So notice that normally this function goes from a smaller value to a bigger value. You can modify this to go backwards instead. But instead of doing this, which we will see how to do later on when we actually get into formal Python, let us explore a new way of going through a list of values. So we start by assigning to the index I the value that we want to start with, namely the minimum of MNN. Remember, we want to start at the largest possible value for I and go backwards. So what we have is a new word instead of for called while. So while, as the English word suggests, is something that happens while a condition is true. So while the I that we are looking for is positive, so while I is greater than 0, what do? We check if I is a common factor. This is the same as before. We check whether I divides M and I also divides M. If we find a common factor, we are done. We just return the value of I that we have found and we implicitly exit from this function. Every time you see a return statement in a function, the function terminates and the value in the return is what the function gives back to us. So we start with I equal to the minimum of MNN and we check whether I is a common factor. If it's so, we exit and return the value of I that we last found. And this is the only value that we need. We don't need any other common factors. So we return the very first time we see a common factor. On the other hand, if I is not a common factor, we need to proceed by checking the next one, which is to go backwards. And this is achieved by this update. So remember that we said that we can assign values or update values using this equality operation. So this equality operation is not mathematical equality as it looks, but rather it is the assignment of a value. So it says take the old value of I and make it the new value. So it says update I to I minus 1. Take the current value of I, subtract 1 and replace it in I. The mathematical equality is written as double equal to. This is what we use in our conditions. So it's important to remember this, that double equal to means equality as in the left hand side is equal to the right hand side, whereas a single equality in Python and on many other programming languages means assign a value to a variable. So this is the final optimization that we have of this naive algorithm, which is to basically scan for common factors from the beginning to the end. So now we are doing it from the end to the beginning and keeping only the first factor that we find. So what we saw in this example is a new kind of loop. So this new kind of loop has a special word while, and while is accompanied by a condition. So long as the condition is true, we do whatever is within the body of the while. Now notice that Python uses indentation, right? So these statements here are offset with respect to the while. So this is how Python knows that steps 1 to k belong to this while. So these are the steps that must be repeated. At the end of this thing, you come back and you check whether the condition is still true. If it is true, you do it one more time, and so on. So while is useful when we don't know in advance how many times we will repeat the steps. When we were scanning for the list of factors, we knew that we would start with 1 and go up to the minimum of m and n. So we could predict in advance that we would do precisely that many steps, and so we could use this for loop. So for loop has a fixed number of repetitions. On the other hand, a while loop is typically used when you don't know in advance when you're going to stop. So in this case, we're going to start with the minimum of m and n, work backwards, and stop as soon as we find a factor. But we have no idea in advance whether this will come early or we'll have to go all the way back to 1, which we know is guaranteed to be a valid factor. So one of the problems that one could face with a while is that we keep coming back and finding that the condition is true. So we never progress out of the while. So long as the condition is true, these steps will be executed and then you'll go back and do it again. So if you have not changed something which makes the condition false, you will never come out. In our previous example, in order to make the condition false, we need I to become 0. So we start with the minimum of m and n. So what we guarantee is that every time we go through this while and we do not finish what we wanted to do, we reduce I by 1. And so since we start with some fixed value and we keep reducing I by 1, eventually we must reach 0. So in general, when you use a while loop, you must make sure that you're making progress towards terminating the loop. Otherwise, you have a dangerous kind of behavior called an infinite loop, where the computation just keeps going on and on without returning a value, and you have no idea whether it's just taking a very long time to compute the answer or whether it's never going to finish. So in this lecture, what we have seen is that we can start with a very naive idea which more or less implements the function as it is defined and work our ways to dramatically simplify the algorithm. Now, one thing from a computational point of view is that though the newer versions are simpler to program and therefore to understand, the amount of time they take is not very different. We are still basically running through all values in principle from 1 to the minimum of m and n. If we start from the beginning, then we will run through all these values anyway because we scan all these numbers in order to find the common factors. In the last version where we were trying to work backwards and stop at the first common factor, it could still be that the two numbers have no common factor other than 1. So again, we have to run all the way back from minimum of m and n back to 1 before we find the answer. So although the programs look simpler, computationally they are all roughly the same in that they take time proportional to the values m and n. What we will see in the next lecture is that we can actually come up with a dramatically different way to compute GCD, which will be much more efficient.